So for this next talk, I wanted to jump just a few abstraction levels to talk about RSocket, which is a network protocol that's in use at Netflix, Facebook, and several other companies. And sort of why this protocol exists and what is it being used for. I do have stickers here, courtesy of Alibaba, who's another RSocket user. So after the talk, if you're interested, feel free to come up here and take some. So communication in the cloud is a challenge, just to kind of set the context. These quotes are from a recent CNCF conference, the Cloud Native Compute Foundation. The network is the unsolved problem of the cloud and open source. We need the network to be a first-class citizen. A standard approach to connecting and communicating with microservices is needed. So enterprises are sort of in transition from the relatively well-known environment of the data center and sort of monolithic applications to this Wild West environment of the cloud. And unfortunately, a lot of enterprises sort of envision this transition as looking something like this, right? That sort of an individual or small set of administrators can manage this futuristic and complicated network of services. Unfortunately, the reality, more often than not, ends up looking more like this. Rather than investing our efforts into building sort of new protocols and new approaches to networking in the cloud, many enterprises sort of invest in taking legacy applications and just transitioning into the cloud. The downside of that is that you're sort of missing out on all the benefits of the cloud. You end up with these sort of clunky architectures that become very difficult to manage. And the costs potentially are huge, right? So when things go wrong, they can go really wrong. Snapchat is a good example. They're spending $500 million a year on cloud infrastructure, mostly going to Google and Amazon. And there's really no reason for this, right? They built their entire application on the Google App Engine using sort of outdated networking protocols. And the result of that is that they can't scale up enough to serve their architecture, and they just have to pay for it. So if it wasn't for this, Snap would actually be profitable. But does it have to be this way? What if instead of 2 requests per second per server, they were able to serve 2,000 requests per second? That's a number that's sort of easily achievable with modest hardware if you don't shoot yourself in the foot. Then their cloud spend might drop from $500 million a year to $500,000 a year, which by any standards is a reasonable number. So it's this kind of problem that motivated the RSocket protocol at Netflix, where I was on the cloud, when I was on the Edge platform team. And this is sort of the reason that a bunch of other companies have invested in RSocket and are started to move forward with it. And it's not to shoot Snapchat, not to attack Snapchat, because modern cloud applications are complex, right? Today's applications deal with problems that didn't exist 5 years ago, 10 years ago. The diversity of users is something that we've never seen before, right? With the emergence of IoT devices, all sorts of different devices, and then different sort of deployment models where your application is not just a back end and a front end anymore. It's sort of this network of interacting nodes. And this sort of the emergence of these different use cases, the new sort of distribution of modern applications, motivates a need for new networking protocols. So back in the day, you could get away with something like TCP and this sort of monolithic architecture where your entire application would be served from sort of mainframe computer. Today's applications have moved sort of far away from this paradigm. So now we're in the days of sort of microservice architecture where you have hundreds or thousands of interacting services. And sort of what new protocols do we need to be able to wrangle the complexity of that sort of application? And this is not just on a diagram. These are literally what some of today's cloud-based applications look like. So I'm more familiar with the Netflix one, but I've heard these referred to as Death Star architectures for obvious reasons. But the number of services and the complexity is almost beyond one person's understanding. in another way of looking at it, so I was on the Edge platform team, which in the case of Netflix was sort of the door, the gateway between 100 million subscribers, at the top of this funnel, at peak, sort of 1/3 of North America's upstream traffic going in, and then that Death Star of microservices on the way out. And we were the team that had to broker the communication between those two different groups. And without something like RSocket, the complexity of dealing with distributed failures or the complexity of building distributed applications just becomes unmanageable. If one of these services fails, it can cause a chain of events that brings down all of Netflix. So RSocket is an attempt by a number of sort of forward-thinking, cloud-based organizations to define a standard approach to connecting and communicating. And it's based on the idea that sort of every application, every distributed application you build has the same basic set of concerns. Things like flow control, service discovery, load balancing, resuming dropped connections, security, metrics, tracing, failure injection. This sort of set of concerns remains relatively consistent no matter what you're building. So why not just bake that into a network protocol so you don't have to reinvent the wheel every time you build a new distributed application? So RSocket is designed to solve this problem at the highest level of abstraction. So it makes no presumption about sort of what kind of data you're sending over the wire, or even what transport protocol you're using. Because RSocket is an application layer protocol that allows you to substitute various different transport protocols. So you could use TCP for some sections of your application. You might use WebSocket or for others, or sort of high performance application protocols like Aeron for others, which is a UDP-based protocol. If you're in a data center, for example. As I said, the origins of RSocket were at Netflix, but now it's sort of heavily used at Facebook. They're in the process of sort of swapping out the underpinnings of Thrift, which is their RPC library. And Alibaba is another user of it. They're also in the process of swapping out the underpinnings of Dubbo, which is their RPC library, to use RSocket underneath. And then Pivotal has contributed heavily to the development. So the next version of Spring, if you're a Java user, will have RSocket sort of baked into the library. So I wanted to dig a little bit more into some of the problems that RSocket is designed to solve, and then take a brief look at sort of the protocol itself, some of the properties of the protocol that allow this to happen. And then I'd like to go into a little bit about what Netifi does, how we're using RSocket to sort of take the abstraction even further. So I think the complexity of modern cloud applications has kind of three different axes, each of which present a number of problems in and of themselves. So first, there's the deployment topology, sort of where your application gets deployed. So it's no longer the case that you can think of an application only in terms of the back-end infrastructure. An application now, in large part, consists of the users because more and more compute power is available not only at the edge, but on a user's device. Right, we're all walking around with computers in our pocket that are more powerful than the servers of a decade ago. There's an increasing desire to make use of that. And then there's the platforms and frameworks that your application is built upon. So what language your server-side logic is written in, what sort of frameworks you're using to deploy it and to manage the communication. And then there's the protocols and interaction models that you want to use. So it used to be the case that applications were mainly sort of request-response based. A user would make a request, the server would sort of process some information and return a response. That's sort of very limiting in these days where increasingly people expect certain degrees of interactivity in their applications. So you not only want to do request response, you want to do streaming data in both directions. And also increasingly this distinction between client and server is something that's vanishing. So not only should a client be able to make requests, they should also be able to sort of receive requests from the system and make information about themselves available. So looking at this first axis, deployment topologies. So in many cases, there's still a data center component, and people are deploying onto sort of bare metal servers. But in addition to that, many people are moving to the cloud, and not just one, but sort of multiple cloud providers. And there's a strong incentive not to be locked into a single provider, because then you end up like Snapchat, where you're sort of at the mercy of their cost increases. So you want to, in some ways, abstract yourself from any particular cloud offering. And then that adds even more complexity if you're using something like Kubernetes, which sort of offers you a layer of abstraction from your cloud provider and allows you to make more efficient use of resources. That becomes sort of another layer of complexity in this distributed application you're building. And in addition to things like that, I mean, there's sort of serverless frameworks like Lambda. You'd like to be able to make use of those, but that presents another complication for sort of the connectivity of your entire application. And then on top of that, there's the frameworks that you're using to deploy your code. Things like Node or Tomcat for Java, Akka for Scala. All of these things were built with generally a particular language in mind, and not necessarily meant to communicate with one another. So there needs to be some sort of commonality between the networking stack that you're using for all these different pieces. And then lastly, there's the protocols and interaction models that are in use by your application. So I mentioned request-reply. So a typical interaction would be a browser making a request to a service. Maybe that exists in AWS. Written in Node, it makes a request to a MySQL database and returns a response. So that's sort of one interaction model that you would typically be concerned with. But on top of request response, an increasingly important and common component in your system would be the streaming interaction model. So I mean, Netflix is a good example of this. In addition to streaming video to users, there's sort of streaming in the other direction taking place. So as you interact with the Netflix website, whether it's on your phone or a web browser, it's emitting a constant stream of information back to Netflix, or telling about what you're doing, and allowing it to make predictions and recommendations for you, and modulate the service that it's providing. So streaming in both directions is an important component. And then increasingly, something like an RPC stack, where you're concerned sort of not only with request-reply, but streaming in both directions. And beyond that, you're interested in very low latency communication. So Netflix, Facebook, many different cloud-based companies make heavy use of RPC, remote procedure call interactions. And typically those are chained together. So you might hit one microservice that fans out 50 other requests to other microservices. And so any one of those going latent can cause delays down the line for your users. And then even beyond that, there's sort of the real-time and peer-to-peer interaction models that are, again, increasingly important, and those come with their own set of protocols as well. So you might use something like WebRTC, which is designed for streaming peer-to-peer interactions among web browsers, or WebSocket for pushing real-time events to your users as they take place. So taken all together, you want to do all this stuff, but the degree of complexity is such that it's really hard to put all this stuff together and actually have it function in any coherent way without reinventing the wheel for every new cloud provider, every new interaction model, every new protocol that you'd like to use. So why isn't there a way that I can sort of write my business logic at a higher level of abstraction and then pick and choose each of these things that I want and just plug it in without completely rewriting my application? So can we do anything about this mess? There's some things that we can't do anything about and we don't really want to, I would argue. One is the deployment topology. I mean, a lot of this is just a consequence of modern applications. They are distributed both geographically and in terms of where you'd like to run the compute. There's a strong case in some cases to push compute all the way out to the edges of your network or even to users' devices. That's designed to solve a problem, so you don't necessarily want to eliminate that. And then proliferation of development frameworks. In many cases, there's good reason to have a diversity of frameworks within your application. Netflix is a good example. A lot of the back-end services are written in Java, but there was increasingly a push by front-end developers to be able to write their applications in Node, because that's what they were more familiar with. Before RSocket, it would have required a large amount of efforts to rewrite the entire Netflix stack in Node. And that's an example of what I was talking about. So like, you don't really want to have to rewrite your entire stack in every single language. You want to do this at a level of abstraction and have implementations that already exist in different languages. And the third, the proliferation of interaction models. Trying to limit yourself to a certain interaction model like request reply is a little like trying to navigate driving through a city if you can only turn right or something. It ends up like multiplying the complexity of your application by many times if you're not able to choose the correct interaction model for the job. But there is something we can do something about, and that's defining the standard approach to connecting and communicating. And this is exactly what RSocket is designed to do. So RSocket is a protocol that allows us to take this sort of finite set of interaction models that I described and provide an implementation across many different languages, infrastructures, and frameworks so they don't have to be re-implemented by each user. So I'd like to go into a little bit of detail about the protocol itself. The RSocket spec is actually very well written and readable. So if you're interested in this, I encourage you to go check out the spec itself on GitHub. But RSocket is a bidirectional, multiplexed, message-based binary protocol based on reactive streams backpressure. That's a bit of a mouthful, so I'll try to sort of unpack that as I go. So it provides out-of-the-box support for these four different interaction models that I described: request response, fire and forget, request to stream, and channel, which is sort of a bidirectional stream where both the user and both the sender and receiver are exchanging a stream of information. So because RSocket is an application layer protocol, this can be expressed as a simple interface. This is the interface as it exists in Java, but it looks very similar in other languages. So basically what you get with an RSocket at the application level is these four different interaction models, and then some methods to help you determine availability for load balancing and things like that. So if I were to make a request response, I would send out sort of payload, which consists of some data and metadata. And then I get back this interesting type, which is a mono payload. And a mono is an implementation of this reactive streams type, a publisher, which is sort of an asynchronous abstraction, something like a future, but it's able to express a stream of information that occurs at some point in the future asynchronously. And then, so fire and forget is a mono void, so it's going to express that it's completed, but you don't actually care about what the response was in this case. So it doesn't have to wait for the receiver to send a response, which lets it operate at a much higher throughput. And then there's sort of request stream, which returns a flux of payload, which is, instead of a single item, it's many items. And request channel, in which both the input and output are a stream. So what is this reactive streams I mentioned? Reactive streams is another sort of industry initiative to provide a standard for asynchronous stream processing on sort of individual instances. So if reactive streams abstracts for asynchrony on a single machine, sort of RSocket is meant to be reactive streams over a network boundary. So the goal of reactive streams is to govern the exchange of stream data across an asynchronous boundary. And the reactive streams effort was spearheaded also by Netflix and involves other companies like Akka and Red Hat, and so has resulted in a very well-defined specification, which is, again, on GitHub, and you can check that out. But this is now, the reactive streams types themselves now exist within the Java language and a number of other different languages. So Oracle has actually taken the reactive streams types and built it into Java itself. So this is designed to be sort of a cross-language way of expressing asynchronous streams of information. One interesting thing that's built into reactive streams itself is this concept of flow control, which is incredibly important when you're building distributed applications. So generally, if you're using like HTTP, you'd be sending a single request and you expect an arbitrarily large response in return. Now, there's nothing to stop the responder from sending you that response at a rate that's much greater than you can actually process it. And that is the cause of many, many distributed systems failures. Sometimes in some protocols, this is handled at the transport layer. So in the case of TCP, that's the case. But the transport layer is not sort of sufficient to protect yourself against this problem because eventually, if you're not able to process this information at the application layer, it's going to fill up a queue and something's going to break eventually. The queue is going to overflow, or you're just going to have to start dropping information. So reactive streams attempts to work around this problem by having sort of communication happening in the other direction. So this pull-push style back pressure, which ensures that data is materialized and transferred only when the receiver is ready to process it. So instead of just blindly sending information, reactive streams has a request end method where the receiver has to request information to be sent from the sender before it's actually sent. In reactive stream, in RSocket, this gets translated into a frame that goes back in the other direction over this bi-directional network protocol, is received by the sender, and then only the requested amount of information is allowed to be sent. So visually, this is sort of the analogy you can think about. So if you're using something like HTTP, which has no concept of application layer flow control, you have to consume data at the amount that it's sent, at the rate that it's sent to you. Otherwise, it's just going to, spill. Your buffer is going to overflow, and you're going to start dropping information. RSocket, on the other hand, because it has messages that are sent in the other direction, never allows the sender to send information at a rate that will overwhelm the receiver. And this avoids, by baking this into the network layer, you're avoiding this entire class of problems. As an application developer, I don't have to think about retry logic or timeouts, circuit breakers, which is sort of a poor man's way of avoiding this problem, and then dealing with things like thundering herds, cascading failure, and all the configuration that's necessary to try to avoid that when I don't have any signal telling the sender to slow down. Okay, so this requester-responder interaction in RSocket is broken up into frames. Like I said, this request end method gets translated into a frame that gets sent over the network, and it gets decoded the other side. This framing itself is binary. It's not designed to be human readable, which allows sort of massive efficiency improvements at the slight downside of being harder to debug, because as an individual, as a human, I can't visually see what's happening over the network unless I decode the frame first. But that's generally the case with most protocols. So that's sort of a small price to pay for order of magnitude level efficiency improvements. And as I said, RSocket is agnostic as to the actual data that's sent over the protocol. It just provides you this binary frame, and you can put anything you want into that, whether it's some binary encoding like protobuf or just text information like JSON. So then importantly, the RSocket protocol is multiplexed over a single connection. So I can make one connection between sender and receiver and then have arbitrary numbers of these interactions across that single connection. And this is another sort of order of magnitude efficiency improvement over protocols like HTTP, especially 1.0, which is not multiplexed at all. And then HTTP has made sort of various attempts to solve this problem, but has never really completely solved issues like head-of-line blocking, where so a large request can prevent subsequent requests from being sent out. So RSocket solves this issue by establishing a single connection and then having logical stream IDs that happen over the same connection And this stream ID gets encoded in a header that gets sent over these frames and then reconstituted on the other side. So it takes advantage of the bidirectional nature of TCP and just adds a framing on top of that. Yeah, and as I said, so RSocket is sort of totally bidirectional. It's not opinionated about who is sending and receiving information. So once this connection is established, either side can act as a server and either side can act as a client. So I can establish sort of a connection between two different machines. From machine A, I can start making requests to machine B, and then B can turn around and start requesting information from A without A, doing anything in advance. Some protocols like HTTP2 sort of make a move in this direction, but even HTTP2 is not capable of this complete bidirectional interaction model, because the server is only allowed to provide information that the client requests. Although they can sort of push information in advance they think the client will request, there's no way for a server to actually make a request completely on its own in the other direction. And then RSocket is transport agnostic. So implementations exist over TCP, WebSocket, HTTP2, and Aeron, and then a few other ones, like there's an in-memory transport and like a Unix domain socket transport. So it's very flexible in sort of what transport layer you use to send the information over. And then the cool thing about that is no matter what transport you use, you get the same RSocket out of it at the code level. So I can write my code against the RSocket abstraction and then go ahead and swap out this transport at a later time, depending on sort of what the optimal transport is for that hop for me within the network. So creating an RSocket in Java is very simple. There's a sort of factory that helps you. But basically it looks like this. You say, I want to connect somewhere. I plug in the transport, in this case, TCP client transport. I give it an IP address, and say start, and it's going to try to connect to an RSocket server on the other side. If at a later time I think I'd rather use WebSocket, I can sort of take that TCP transport, make a one-line code change, and without changing any other part of my application, I've completely swapped out the networking stack, but I still get this RSocket back. And then if I want sort of an RPC style interaction model, I could use something like protobuf, for example, to do to generate code to do RPC. So this is an example of using RSocket RPC, which is another open source RSocket protocol or open source project within the RSocket GitHub domain. So this is achieving something very much like gRPC achieves, but using RSocket. So you just define a service using, in this case, protobuf. It generates this code for you, the RSocket service client. And then you're taking the RSocket that was created sort of in the previous slide. I can just plug that in, and then I have RPC over a network boundary. And because of some of the efficiencies I was talking about, this is about 2 to 4 times faster than gRPC, I think. Which makes use exclusively of HTTP2. So I wanted to talk a little bit about this idea of a service versus a protocol. So like why is RSocket a protocol and not just a collection of services? There's interesting analogies to draw within other domains. And it's interesting to compare sort of a service-based approach to a problem versus a protocol-based approach to a problem and sort of explain why one is better than the other. So Napster, some people might remember that for transferring files. So Napster was a service-based protocol. And the downside of that, obviously, is that it can be shut down. Versus BitTorrent is a protocol, right? So anybody can participate in BitTorrent if you're able to speak that protocol. And that sort of gives you this distributed architecture and provides certain guarantees, like there's no single point of failure. Another domain is transferring money. So things like Western Union or PayPal are sort of service-based approaches to money transfer. But this sort of interesting new approach in Bitcoin, which is the protocol-based approach. And by baking certain things into the protocol, you're able to provide guarantees out of the box about how that service operates, right? So with Bitcoin, it's not susceptible to things like currency manipulation that you can do with regular cash. And then there's sort of the connecting machines problem. So back in the early days, of the internet, there was things like AOL or Prodigy, these service-based approaches to connecting to the internet. Those sort of disappeared once things like TCP routers emerged. So anybody is familiar with the history of the internet. This is the Stanford Blue Box, which is sort of the precursor to Cisco's first multi-protocol router, which sort of was the start of the internet. So by analogy, sort of for connecting cloud services, there exist already a number of different service-based approaches to this, things like Envoy and Istio. So Envoy is sort of a sidecar that's designed to attach to your legacy applications and allow you to easily move it into the cloud. And then things like Istio are like a collection of services that allow those sidecar-based applications to discover each other and communicate. That's the service-based approach, but RSocket sort of represents the protocol-based approach to this connecting and communication among cloud services. And Proteus is the Netifi project that sort of takes advantage of RSocket and lifts the level of abstraction to this cloud-based communication. So I want to go into a little bit about what Proteus is and how that's designed and how it uses RSocket to achieve that. So from the previous slide, this is how you would create a regular RSocket, say, in Java. But if you look at this in a little bit more detail, there's some problems with this approach. One is that this IP address is in there, which is sort of a transport-specific piece of information that I would need to know in order to create this RSocket. And this, seems relatively innocuous, opens up this whole other set of problems. Say I have, the Netflix Death Star architecture, and I've got 500 different services, each of which might have hundreds of instances within the cloud. How do I know what IP address to put in there? It ends up being a very complicated problem. At Netflix, entire systems were dedicated to just transferring lists of IP addresses that you could connect to. And then you need to know, not only does it exist, but is it healthy? So I need to start pinging those services and have sort of registries with health checks that keep checking the status of that service and figure out whether it's up or down. And then you get into weird problems. If a service goes down, it still appears in the registry. Is it still viable to connect to? Then you have to figure out whether you want to be optimistic about that or pessimistic. It opens up all these different problems, right? What Proteus tries to do is abstract that completely, but still keep the RSocket boundary. So what Proteus gives you is a way to sort of instantiate these virtual RSockets that take care of all those problems of service discovery, connection, load balancing across all the instances that might service your request. So instead of knowing which IP address to connect to, with Proteus I can sort of connect into Proteus, which is sort of equivalent to a TCP router, and then just say, I'd like to talk to service 1. And I don't know where that exists within my network. I don't know its IP address. It might be on a different server within this cloud. It might be in my data center, or it might be running in somebody's web browser. But as an application developer, I no longer have to care about that. So that's really cool. So how does that actually work? So like I said, Proteus is sort of equivalent to a TCP router, but for microservice communication. So within your network, whether it's in your data center or in a cloud environment, you might run several of these Proteus brokers. They communicate with each other and form sort of a cluster. And then to any node within this cluster, I can start to connect services. So I might connect a service that I've written in Java or another one that's written in Node. And notice that these services don't have to care what language they're written in. Right? Like a Java service can talk to a Node service with no knowledge of the internal implementation details. And then once I connect to Proteus, all the traffic flows over this bi-directional RSocket. So I can connect in and immediately start to handle requests inbound to me over this connection that I established outbound, and vice versa. So there is no client and server distinction. So likewise, I can connect in from a web browser or a mobile phone and start to make requests, and also start to sort of receive streams of push-based information if that's what I want to do, or dump streams that get diverted into a data processing pipeline. And all of this without sort of any infrastructure to deal with service discovery, load balancing. All that's taken care of by this Proteus broker. So in addition to this, I can also use RSocket to investigate the state of this network of services. So at Netifi, we have sort of a web-based control panel. You can go in real time, see what services are available within your network, and then see visualizations of these services and sort of real-time traffic that's flowing through all these different nodes. And even beyond that, I can start to connect in things like open tracing or a metrics backend like Prometheus. And again, in real time, I can start to stream information and record this so I can go back later and see, for each of these services, how are they performing over time? What does their latency profile look like? For an individual request, even what path did it take through all these different services? And these sort of like observability and visualization tools are really critical for building resilient networks of services. So as I said, RSocket is sort of an order of magnitude more efficient than existing services out there. This is a little too small to see, but compared to something like Istio-based approach, I think on last count it was 10 to 15 times higher throughput, and the latency profile essentially looks flat. So the 99.99th percentile of requests took no more time than the 99th percentile. And if you build distributed applications, it's this like tail latency that kills you when you're building distributed applications, especially when you're fanning out calls to a number of different services. Eventually, you're going to hit this tail latency, and your user is going to essentially experience whatever the 99.9% percentile of latency distribution that your application has returned. And then, in addition, so the setup of Proteus is designed to be more or less equivalent to the setup of a TCP router, in that you give it a few configuration details, set it up once, and sort of forget it's there. It becomes part of your network. And this is in sharp contrast to the more service-oriented approach of something like Istio or a service mesh, where that requires you to go in and for every service configure lots and lots of properties of that service to do with circuit breaker parameters or health checks, etc. Proteus takes the approach of building that all into the network protocol, into RSocket. So there's really nothing to configure. And then again, because it relies on sort of the reactive streams APIs, which gives you this nice DSL for stream processing, there doesn't have to be a whole separate API for if you want to do push notifications, for example. If I wanted to do that without RSocket, I'd have to learn some completely different API like PubNub, or invent my own sort of API that runs over WebSocket or something like that, that I have to create myself. So if you're interested in this stuff, I really encourage you to check out our website, netifi.com. There's some quick starts about getting up and running with Proteus. So Proteus is free to use as a community edition that anybody can start to play around with, and there's quick starts available for Java, JavaScript, Spring. As of recently, there's a .NET implementation. As of today, actually, we just released the .NET implementation of RSocket. So that's something I encourage anybody who's interested to play around with. RSocket open source is, as I said, there's a number of different companies that are contributing to RSocket, and there's implementations that exist in a number of different languages. The ones that are sort of the mainly used are Java, JavaScript, and C++, which is heavily used at Facebook. And then the .NET implementation is something that we've created and just open sourced. There's also a Kotlin implementation if you're an Android user, which I didn't put up there. There's also RSocket RPC, which is sort of the protobuf code generator. It's not limited to protobuf. I think that's the main one that's out there right now. That's interesting as an alternative to something like gRPC. And then sort of our Netifi specific open source projects, in addition to the Proteus client, there's things like Spring integration and then an HTTP gateway, which lets you bridge into HTTP, which is not a protocol that's supported by RSocket because it's request reply only. But this lets you bridge into sort of legacy applications. And with that, I wanted to leave some time at the end for questions. So thank you for coming again, and I'm happy to take anybody's question. Oh, perfect.
So this way you don't have to yell.
Thank you.
So how are you handling throughput, quality of service if you're multiplexing all of these streams? How are you setting priority for different message classifications?
Yeah. That's not built into the protocol itself, but the protocol is.
Repeat the question?
Yeah, sorry. The question was, if RSocket is multiplex, how you're handling quality of service for the various streams that are multiplexed within that single stream. Like, is there any concept of priority for individual streams? That's not built into the protocol itself, but the protocol is designed to be extensible. So if you wanted to define that, you could define an extension to RSocket that expresses the concept of like stream priority and do it that way. I didn't really cover some of the other stuff that's built into RSocket to do with quality of service. One is this concept of leasing. So this is a way for a server, not just with, so the concept of back pressure exists within like an individual stream that happens over that multiplex channel. In addition to that, there's this concept of leasing, which applies to the channel as an entirety. So a server can asynchronously say, like, all right, I'm ready to handle like 1,000 requests in the next second or something, and that those leases expire if they're not used. So you can use that to reduce the amount of traffic that's being sent to you if you're having some issue, or for example, if you're a Java server and you know a garbage collection is going to happen in the next second, you can start to reduce the leases that you're sending out, allow that garbage collection to happen, and then sort of increase it again. So those kind of things are built into the protocol. The other thing that's built in that I didn't go into much, but is heavily used at Facebook, for example, is resumability. So if, for whatever reason, my connection gets dropped, like I'm on a mobile device and I switched applications or I went into a dead zone, each of those streams has like a resumption ID attached to it. So I can go in and say, like, I got disconnected, but I want to resume the state of this stream, and here's the ID that I had associated with it. Then from the back end, you can sort of wire things up again. So the back end service that was fulfilling that request doesn't even need to know that that disconnection happened.
And so you have a service basically that exists above the concept of the connection between them.
Yeah, exactly. Yeah. So I mean, RSocket, because it's totally bi-directional, it's really cool. You can do stuff like that just is not possible with other protocols. So I can sort of retain this virtual RSocket, and then once the other side exists, again, I can wire everything up. That's another thing that Proteus does, for example, is it allows you to make requests to this virtual RSocket before there's actually anything on the other end to handle it. And because all the APIs that are exposed are asynchronous, they all expose these reactive streams types, I can sort of just delay the request being even sent to the person who's going to handle it until they're available. And all of that is sort of totally within the bounds of this reactive stream. So I could make a request, and then 2 minutes later, when that service is actually available, I might get a response. But I don't need to preemptively fail and then have that person deal with retries. I can just wait until that resource is available. But thanks. Yeah, good question.
I was wondering if you could comment on using this with like peer-to-peer stuff, IPv6 and decentralized things.
Yeah, if you check out like the Netifi GitHub, there's some really interesting demo about a chat server that's sort of completely serverless. So it's going through the Proteus broker, but it's all implemented in terms of web browsers that are just connecting among themselves. One of the things that's built in is service discovery, right? So I can, as different users connect into this, to the Proteus broker, they make their own services available, and then web browsers can call services on other web browsers just as easily as they could call services on a client. So I think in that sense, like RSocket is really well suited for sort of this peer-to-peer distributed application.
If you have legacy applications which are using the current models, communication models, and you want to move to this RSocket or Proteus model, how much effort does it take? Depending on the complexity of the application.
Yeah.
So the new one is great, but there is a ton of stuff out there. If they want to leverage this, what path would you take?
Yeah, a lot of it depends on like how you've architected your code, I suppose. But I mean, in most cases, you're not concerned about the transport that you're using. Like, even if you're using HTTP, usually you're wrapping it in a client library or something where there's some kind of service call going on that then gets fulfilled by an HTTP request. So because it's an application layer protocol, it lets you plug it in like at that layer, so you could swap out the internals of that service call and implement it over RSocket. If you're sort of committed to, if you have legacy stuff that you just can't change at all, like at the application layer, that was the impetus behind something like this HTTP gateway, which just lets you bridge into legacy services, both inbound and outbound, using HTTP. But there's all various other mechanisms exist. Like if you're running an application in Tomcat, for example, you're in a servlet container, that can still do RSocket via WebSockets, because sort of modern versions of Tomcat support WebSockets. So you can plug it in that way and then support both HTTP and RSocket if you want to. So there's various strategies for bridging it. Another one is like a sidecar-based approach. So you could conceivably run this through a sidecar, which then communicates like locally to your service.
Just one follow-up. So for example, at Netflix, when you have to migrate from the older to the RSocket model, how much effort did it take?
In the Netflix case, so the API server that was sort of in the middle of that funnel was dealing with most of the complexity. So that we sort of built this serverless platform where teams could go in and write business logic in Groovy, which it was all based on the JVM. But then a number of teams wanted to move to Node, for example, and start writing that in Node. And so that part changed for them, but nothing sort of underneath that API layer had to change at all. So they could take their business logic that they had previously written in Groovy that ran on that serverless platform, and then move it to a Node application that ran in something like Mesosphere.
So is Proteus kind of a distributed model? You kind of put up there an image with everything running through kind of this Proteus router. Does that handle all the traffic, or is this distributed in some way with other Proteus routers, and do they communicate that way?
Yeah. So it's broken up into like clusters. So I can make a scalable cluster of Proteus routers, and they communicate among themselves. I can then sort of have different clusters that talk to one another. So I might have one cluster running in like US West, another in US East, or another in the EU, and I could sort of communicate. I can have cross-cluster communication that happens across those clusters, or I might have a cluster for like each team within my organization. And sort of that's another product that we're working on is a cloud-based sort of management and connectivity for all of the clusters, so you can define rules about how you want traffic to be routed across all those different clusters. But because, I mean, each broker is capable of handling some millions and millions of RPS, typically the cluster size for your particular organization within your company might be pretty small, but then you might want to connect those together. And then the other thing it deals with is like access control across those different clusters. So you can set up clusters for a team and then give access to other teams.
One other quick thing. As far as the clients go, or anybody connecting to the Proteus service, does the Proteus service do health checks and maintenance? Do they determine which protocols are supported on the clients? If it's just TCP, if it's WebSocket, how does it determine how to connect to those clients?
Yeah, so there's kind of a bootstrapping mechanism that goes on. So the client needs to know initially how to connect to any Proteus broker, and then from there it will stream information about other brokers that are available that you might want to connect to, and then it establishes sort of a connection pool across all the brokers that are available to it, or some subset of them. And that initial bootstrapping depends on the environment you're in, but it can say if you're using like console, it can use console-based service discovery. If you're in AWS, it might use like tags to discover an initial broker. So we have a number of like integrations built in for console, Kubernetes, or Pivotal Cloud Foundry, just to handle that initial like connection. Great, thank you. Oh, okay. I think it's 8:30, so I guess we're just about out of time.
Look like we're almost out of time anyway. Any more questions over that side? That side is pretty quiet today. Okay. Well, thank you very much.
Thank you.